Good morning, all. Hello. Audible ആണല്ലോ? Hello.
Audible, sir.
Okay. So നമുക്ക് start ചെയ്യാം. Welcome Divya Miss and all other participants. നമ്മൾ ഇന്നൊരു ഓൺലൈൻ FTP കണ്ടക്ട് ചെയ്യുകയാണ്. Introduction to Verilog HDL. സോ അതിന് ഞാൻ ആദ്യമായി ദിവ്യ മിസ്സിനെ ഈ ഒരു സെഷനിലേക്ക് സ്വാഗതം ചെയ്യുന്നു. എല്ലാ പാർട്ടിസിപ്പൻസിനെയും ഈ ഒരു സെഷനിലേക്ക് സ്വാഗതം ചെയ്യുന്നു. ഞാൻ ആ സെഷൻ ഞങ്ങളുടെ HOD രതി സാറിന് ഹാൻഡ് ഓവർ ചെയ്യുകയാണ്. സാർ.
Good morning to everyone. So before beginning this FTP, let me welcome Miss Divya, Assistant Professor, 𝗙𝗪𝗠𝗍𝗍 College of Engineering. Welcome you, ma'am, and thank you so much for accepting our request to conduct this FTP. And of course, welcome to all other faculty members and research scholars also who have joined us for this FTP. I'm not taking much time, so let me hand over this session to Miss Divya to start with the FTP. Divya, ma'am, please.
Okay, very good morning to one and all. Am I audible? PRAJEESH sir?
Mr. കേൾക്കാം.
So, very good morning to one and all. Actually, it's my privilege and honor to be here to handle this one-day online FTP on Introduction to Verilog HDL, conducting in Mahaguru Institute of Technology, 𝗙𝗏𝗍𝗏𝗏. So, for this, actually, I would like to thank Professor PRAJEESH, coordinator of this program, and HOD of EC department in Mahaguru Institute of Technology, and all the staffs who supported PRAJEESH sir for the smooth conduction of this event. Thank you all. So, shall we start the program? Shall we start the session?
Okay, Mr. Thank you. Start here.
Okay. Screen കാണാൻ പറ്റുന്നുണ്ടോ? PRAJEESH sir?
ക്ലിയർ ആണ്.
Okay. So, in this session, I would like to give you the introduction about HDL. What is HDL? Hardware Description Language. Why we are using this hardware description language for the current electronic device design? Or what is the need of this hardware description language? And here we will discuss all the syntax and different levels of abstractions used in Verilog HDL. And finally, we will study how to code a given digital circuit using this Verilog HDL, Verilog Hardware Description Language. So, before going to the coding and all, first of all, we should know what is the need of these HDL languages. Why we use HDL languages for the coding of digital circuit design. So, I will give you a brief introduction about this domain. Then we will go to the syntax and Verilog features, and finally we will see how to write the coding of this digital circuit design. So as you all know that as the technology getting improvised, device size also getting reduced, right? So as the technology increases, technology gets improvised, device size reduces, but at the same time it doubles the capacity. That means even though the size getting reduced, the number of applications or functionalities increases for every generation. So how can we establish this? We have to increase the number of components incorporated onto the chip. That is, based on that only we have this IC classification such as small scale integration, MSI, that is medium scale integration, LSI, VLSI, then ultra large scale integration, super ultra large scale integration. From this slide, it is clear that as the technology getting improvised, what happens is the number of devices incorporated onto the platform also getting increases, and its application functionalities also getting increased. Okay, so consider one example. Earlier days we have desktops in our home, then later it replaced with laptops, then tablet scale, then nowadays we have smartphones. So in future we may have small chips which can be incorporated onto our fingertips, and it could be able to function like a supercomputer. So actually the same thing predicted by the scientist Jordan Moore several years before. What was his prediction? Yes, integration complexity doubles for every 2 years. So the main objective of the VLSI technology is nothing but miniaturization of the device. That is, reduce the size, then double the capacity and half the power consumption rate. So what I am trying to convey you is, for every generation, circuit complexity increases. Then the design will be highly prone to errors. Okay, so checking the entire design manually before the actual fabrication process, that would be a time-consuming process. So that means as the circuit getting complicated, it will be more prone to error. So it will take more time for the circuit debugging and all. So if you handle digital electronics lab, you know the circuit of 4-bit up counter. It is a very small circuit, 4-bit up counter. So when you wire the same counter circuit on the breadboard, you know how does it look like. If you are getting the output first time itself, then everything is fine, right? So if it's not working properly, then you know how much complication is there in its troubleshooting. If this is the case for a very small circuit, then can you imagine how hard it is to go ahead with the huge complex circuit design? So what is a remedial solution for that? Yes, everything should be automated. So we go for this computer-aided design tools or electronic design automation, EDA tools, where we can check the design. The digital circuit can be checked with the help of hardware description language prior to the actual fabrication. So as the complexity getting increased, it is very difficult to debug everything manually. So we go for this hardware description language. So hardware description language is nothing but it is high-level language or it's a computer language used to program electronic and digital logic circuits. So by using these HDLs, at the earlier stage itself, we can debug the design, or we can correct the errors. If some errors occurs, we can correct it at the initial stage itself. Then we can reuse that design. Then By using this HDL, we can have better and easier design verification. So popularly used HDLs are Verilog HDL and VHDL. VHDL is 𝗏𝗍𝑠𝑖𝑐 HDL. That is very high-speed integrated circuit hardware description language. Other popular HDLs are System C, System Verilog. System Verilog is nothing but the advanced version of this Verilog HDL. So here in this session, we will see how to code a given digital circuit using Verilog HDL. So actually, this is a VLSI design flow which is used for the current fabrication process. First of all, designer or the customer will give the system specification or design specification. Based on its behavior, we will write the program. Then we will write it in model sim, or you can use, if you want, you can use Silence tool or lattice diamond tool is there. So many open source are available that supports this Verilog HDL, that supports this HDL languages. So you can use any of that tool to write this programming. Then after that, in that tool, it will generate a gate level list. It will generate its gate level diagram. Okay, and each and every step verification is there. So that the advantage is that at the final step, it will be error free, or we can reduce the error at the final stage. After so many verifications and all, finally it goes to actual physical design or actual IC design. Then it goes to the next step, that is the final fabrication process. So in Verilog HDL, it has got mainly 4 types of modeling, such as behavior level, data flow level, gate level, switch level. That means if you want to design a small NOT gate using Verilog. Okay, so a NOT gate is given to you. NOT gate is the digital circuit given to you, and you are asked to write the Verilog code for the same. So you can write the Verilog code for the same NOT gate by using any of these 4 modeling types. Either you can use behavior level, or you can use data flow level, or gate level, and the 4th method is switch level. Behavior level means you are writing the program of the given circuit based on its behavior. What is the behavior of the given circuit? Based on that, you are writing the program. Then data flow model. Data flow level means where you will look how does it functions. That means what is the actual functionality of the device, or how the data flows from input to the output. And gate level is you are converting the given circuit based on its logical level diagram. And by specifying here in this circuit, we are having 1 AND gate, then 2 OR gates. Okay, so you will instantiate, or you will specify these gate as such in the gate level modeling. Then switch level is nothing but you know that these gates are made by nothing but the switches, okay, or transistors. So you can again convert it into smaller level of abstraction, that is nothing but the transistor level of modeling. Transistor is nothing but its switch. Transistor can act as a switch. So for the given circuit, you can write the code by using this switch level modeling. So from this slide, it's clear that for a given digital circuit, if you want to write the Verilog HDL code, you can write it in 4 methods, either by behavior level, or by data flow level, or gate level, or switch level. the following slides, we will see how can we write the program by using each type of modeling. Okay, so this behavior level is the highest level of abstraction. That is based on the behavior only we are writing the program, and we are dividing the top level into next level, that is data flow. Then again the same device is converted into logical gate circuit. Then the very lowest level of abstraction is the representation of the given circuit using transistors or the so-called switches. So now let's see how to what are the Verilog features. How to start with this Verilog HDL. How to code a given circuit using Verilog HDL. Okay, so let me explain these modules and all using a digital circuit. Then I think it will be more clear to you. Can you see this, producer?
Yes.
So I think all of you know what is NOT gate. It's a very small, very basic component in the digital circuit, and its circuit symbol is like this. So when you give A as the input signal, the output will be A bar. If you are taking B as the output variable, then you can write B equal to A bar. So how to write the Verilog code for this NOT gate? Okay. So, so the basic component used to code the given digital circuit using Verilog HDL is called, the basic unit is called module. You are representing, you are coding everything inside this module. Actually, it is called the basic building block in a Verilog HDL. Okay, inside this module, we are writing the code for a given digital circuit. Okay, so what are the procedures to be followed to write the code for this NOT gate? So the first thing is that you should write a module for a particular design. Okay, so when you write the code for every digital circuit, it should contain two blocks such as design block and test bench. Okay, so when you write Verilog HDL code for a given digital circuit, it should contain two parts, two blocks such as design block and test bench. Okay, in this design block, we can write the functionality of the given circuit. Functionality of the given circuit can be written in this design block. Then what is the requirement of this test bench? What is the function of this test bench? It will test, it will check whether the given design is working properly or not. Okay, so test bench is to test the given design block. Okay, so the actual functionality of the circuit will be written in this design block, and in the test bench we will apply test input vectors. We will apply test input vectors so that it will test whether the design block is working properly or not. Okay, so after writing this code, after writing this design block and test bench, how can we test, how can we simulate the same design? Then we will see how to code. Okay, so when you write using Verilog HDL, just a minute. This pen is not working properly. Okay, let's continue. Sorry for the inconvenience caused. So our topic was how to write the Verilog code for a uh, given digital circuit. So it must contain two parts such as design block and test bench. Then in the design block, we will write the functionality of the given design. So that functionality can be written either by using behavioral model or by data flow or by gate level or switch level. Okay, and test bench is nothing but it is the simulation unit. It will test whether the design is working properly. It is to test whether the design is working properly or not. Okay, so after writing this code, this VHDL code, we can write it in either we can write it in model sim, or you can use so many open source are available that supports HDL languages. So EDA playground, or you can use lattice diamond and ultra quartz software is there. Then silence Vivado is there. So out of this, the first three, in these tools, you should write the design unit. You should write the design unit and test bench. Then you can simulate the design and check the design is working correct or not. Okay. In the last two, 𝗙𝗏𝗏𝗏𝗏 and 𝗙𝗏𝗏𝗏𝗏𝗏, both are used for the synthesis tools. Okay, so there you need to write the design unit only. In these cases, you can write the design unit of the program, then you can compile that, then you will synthesize the design, then you can connect that design or you can burn it on the FPGA kit. There you can obtain the output result. Okay, so the first three tools are the simulation tools, where you should write the design unit as well as test bench. Then 𝗙𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏 or Spartan versions are available. So in those tools, only need to write the design unit. Okay, then that design unit will be compiled, synthesized, and finally interfaced on the FPGA kit. So this FPGA kit, it contains CTLD block, so it will be configured according to your design. FPGA, in FPGA you can configure the it is reconfigurable, so the design can be programmed. The design can be reconfigured in the FPGA kit, and finally you can obtain the output in that FPGA kit. So first of all, you should compare it in 𝗙𝗏𝗏𝗏𝗏 or 𝗙𝗏𝗏𝗏𝗏𝗏. So today we will see how to write the code using this EDA player. For that, I hope that you all are having laptop with you with internet facility. So in a net is required for doing HDL programming using EDA playground. Okay, and here in our lab we are using this ModelSim software. Actually, student edition, it's available for 6 months. ModelSim student edition is there. It's available for 6 months, but due to some network issues and all, currently it is not there in the. It is not available in the net. So we can't download currently from the ModelSim site. They are showing the message that it will be recovered soon. So if you want, you can do the programming using this ModelSim software also. It is a open source. It is available. Its cracked version is available. Okay, so first of all, we will write the design unit or test bench using ModelSim or EDA playground or Lattice Diamond or Quartus or Vivado and so on. So where you will write the program and you can simulate or synthesis. Okay, and finally the output can be obtained through the FPGA board. Okay, if you are doing simulation, if you are using simulation tool, then you should write the design block as well as the test bench. But for the synthesis, there is design block where we can use only the design block. Okay, so now let's see how to write the program of the digital circuit using this Verilog HDL. So we discussed that in the So now let's see how to write a code for NOT gate. So first, let's see how to write the design block for the NOT gate. Take A with the input and B with the output. Then design block. So it should start with a keyword called module. What is module? The basic building block or basic building component of the 𝗓𝗏 HTML is called a module. So, and also 𝗓𝗏 is case sensitive. Case sensitive. So, all the keywords should be specified in lowercase letter. All the keywords should be written in lowercase. So now let's see how to write the 𝗓𝗏 code using 𝗓𝗏 code of a NOT gate. So module should start with a keyword module, then module name. So let the module name be my node. Okay. So don't write the name as node. Why? Because is the basic gates node and or everything is well specified, well written in the standard library of this model cell or in that simulation tool itself. So if we write node, instead of this my node, if we are writing node as such, it will show some error messages. Okay, so use the module name as any other name of the basic gates as such. So let the name be module my space module name, then in bracket write output comma input, or you can write input comma output. So the syntax to be followed while writing the design block. First line is module declaration. So it should start with a keyword module, then module name, then this is called port list. Port list, and it should be terminated with a semicolon. Every line should be terminated with a semicolon. Module name, then port list. For every design block and test bench, the first step is to declare the module. So the syntax to be followed for writing the module declaration is module, that is the keyword, then module name, okay, then port list should be terminated with a semicolon. Okay, then the next step is port declaration. Okay, when you write the design block, the first step is module declaration. The syntax to be followed is module space module name, then port list. Then in the port declaration, the second step is port declaration, where you have to specify the input and output ports. Here in our design, we consider B as the output signal and A as the input signal. So, in the next step, we should declare all the ports used in our design. Okay, so for specifying port, whether it is input port or output port, we should use the keyword in small letters. Why? Because this verilog is case sensitive. So output space B. And what is our input? A is the input signal. So input space A. So there completes the port declaration of our circuit. Port declaration of our circuit. Okay. Then the next, what is the next step? The third step to be followed is define functionality. That means we have to write the function of the given digital circuit using any of the four modeling styles. That means either you can use behavior style or data flow or switch level or gate level modeling. Okay, now let's see how to write the program using data flow, because data flow is the easiest one as compared to other three. So we will see how to write the Verilog code for NOT gate using data flow model. So the third step, what was the third step? The third step was define functionality of the circuit. Define functionality of the circuit using any one of the four modeling styles. Okay, so here let's proceed with the data flow modeling. So in data flow model, the syntax to be followed is use the keyword assign. It's a continuous statement. That means it defines how does the data flows from input to the output. So use the keyword assign. Assign. What is our output signal? It is B. So assign B equal to negation of A. For negation operator, you can use this symbol. Okay, assign B equal to negation of A, or you can use this exclamatory mark, that is like this, negation of A. Either you can use assign B equal to this unary operator, or you can use this exclamatory symbol for the operation, so-called inversion. Okay, so assign B equal to negation of A. So in that single step itself, it is clear that the output of the output signal, that is B equal to the inversion of A. Like input signal invert that signal will be obtained. That signal will be assigned to the output signal. Okay, so where completes the definition for the circuit functionality. There is small inverter circuit done. So by using a single step, where completes the functionality definition. Okay, so final step is terminate the module. The final step. So when you write the same block, 4 steps to be followed. First step is module declaration. Module declaration. The module declaration, we should write the keyword module as such in small letters. Then module name. Okay. Then port list. What all ports are used in the given circuit. Okay. In Verilog HDL, it supports 3 types of ports, such as input port, output port, and in-out port. Okay. So input and output port. These two ports are in-out port is bidirectional. Okay, you can use this in-out port as input as well as output. Okay, so now it is used for declaring the interconnections of the given circuit. And input and output port, those ports are unidirectional. In-out port is bidirectional. Okay, so here in this circuit, in our inverter circuit or not circuit, we have used two types of ports such as output port and input port. Okay, so the final step to be followed while writing the same block is terminate the module. Okay, so you can terminate the given module by using the keyword as end module. End module should be written in lowercase. Why? Because it is keyword. So you can terminate the module by using the keyword end module, and the letters should be written in lowercase only, and there is no space between end and module. Okay, so there completes the design block of inverter circuit. Any doubt?
No, let's continue.
Okay, so we have one inverter circuit and we have written the design block. So the steps to be followed are, what are the steps? Module declaration, then code declaration, define functionality, terminate the module. So module declaration means module name, then port list. So this is module declaration. Then port declaration, where we should specify the ports output B, input A. So these two steps that gives port declaration. Then the third step, define functionality using any of the abstractions or any of the modeling styles. Here we have used Dataflow modeling. Okay. Then the final step is terminate the module using the keyword end. Okay, so now the next step is, what is the next step? We should write its test bench, or it is also called simulation unit. Okay, so the steps to be followed while writing test bench are module declaration, port declaration. These two steps are one and the same that we have used in the design block. The design block, we have the first two steps were module declaration and port declaration. So the same steps should be written here also in the test bench, that is module declaration and port declaration. Okay, and the third step is calling design under test. That means calling this design block into this unit. That process is called instantiation. So instantiation that our process just to connect the design block as well as the test bench. To link the design block and test bench, we are using a step called instantiation in test bench. Okay. Then the next step is applying test vectors. Then display the result, terminate the module. Okay. So let's see how to write the test bench for this design of NOT gate. So next, let's write test bench for the given set. So first step is one and the same, module declaration. What is syntax? Module space module name. So since it is the test bench for the NOT gate, let me write the name as my NOT underscore TB, or you can write my NOT underscore test. Okay, so if you are writing or if you are considering the same ports, the same name in the test bench also, then no need to write port list over here. That means, suppose I am taking the same values B, A. Same B, A, no need to write the signals or the ports over here in the test bench. Suppose you want to assign a different name. Let it be capital B and capital A. Then it should be given, it should be written in the test bench. Got the idea? If we are using the same port list in the test bench also, no need to write the port list here in the test bench. Just write module space module name. Module name. Okay, I am in the test bench B, A theniyanu ports aayittu use cheyyunnathu. Okay, then the next step is port declaration. So already we have clearly specified B and A are the outputs and inputs in the design block. So our step up, no need to repeat that steps in the test bench. Okay, but you should specify these signals, whether it is a wire data type or it is a registered data type. Verilog supports so many data types. So I have included all those things here in my slide. So later you can go through this. Verilog supports so many data types such as registers, then nets, then so many operators, relational operators, bit-based operators. So you can go through these Verilog features for knowing the syntax in detail. You can refer introduction to Verilog HDL by Samir. So your text just refer that. Even for a beginner, this is very useful. Clearly, all the things clearly, syntax with examples clearly written in this textbook. So, if you want to practice more and more, you can refer this textbook, Introduction to Verilog HDL by Samir. Okay. So, anyway, Verilog supports so many data types such as integer data type, then parameters, strings, register, nets. So when you write a port, input port or output port in the test bench, you should clearly define the signals such as input signal and output signal should be declared as either register data type or register data type or net or so-called wire data type. Okay, all the ports, if it is input port or output port or in-out port, it should be clearly declared either as reg data type or wire data type. Okay, so wire data type means it just assign a value to that particular signal, whereas reg means it will stores the value for a particular duration. Register means register is a data type where it stores value for some time. Okay, and wire means it just passes the value. Okay, so when you write the 𝗩𝗏 programming, all the ports should be assigned either as register data type or wire data type. Okay, so when you write the code, how can we declare the particular signal belongs to register or wire? For that, we should know the 𝗩𝗏 block clearly. That is, see, so already we have discussed that we have two blocks. We have two blocks, the same block, and test bench. Okay, so test bench where we are writing the functionality, and here test bench we will apply values to input signal. Input signal value കൊടുക്കുന്നതാണ് test bench. Okay, so when you write the program for a inverter circuit and when you simulate it, actually what is happening over there? In the test bench, we are applying test vectors or input values. So, with respect to that applied test inputs, it will link the design instantiated over here. Number test bench number step use so-called instantiation. Instantiation is nothing but connecting design block and test bench. Okay, so with respect to this applied test vectors, it will go to that instantiation step. Okay, so in that instantiation step, we have written the module to be tested. Here we have my node, so we will see how to write that instantiation. So ഞാൻ ഇപ്പോൾ പറയാണ് ഇവിടെ നമ്മൾ മൈനോട്ട് എന്ന് പറയുന്ന ഇൻസ്റ്റാൻസിയേഷനിൽ നമ്മൾ ഡിക്ലെയർ ചെയ്തിരിക്കും. So when you apply test values, it will go to this instantiation step where we have written the module name mynode. So it will go to that block. That is our actual design block. Then in that design block, we have written the circuit functionality. That is assign B equal to negation of A. So, this A value, we will apply it. Test bench. So, it will connect the design block. Design block and A value applied to final output. Okay, then the final output value will be obtained at output port, and that value will be displayed over here. So number block number design block and test bench. So in the test bench we are applying input values. With respect to that input values, it will check the instantiation step. So our number where we have written the design block to be tested. So our design block point where it will apply the input values into the Boolean functions or the circuit definition that we have written the design block. Then finally, after logical operations, the final output will be assigned to output. So our output value display in the test bench. So, നമ്മൾ ഏതൊക്കെ കോഴ്സിനെയാണ് വയർ ആയിട്ടും രജിസ്റ്റർ ആയിട്ടും ടെസ്റ്റ് ബെഞ്ചിലും ഡിസൈൻ ബ്ലോക്കിലും ഡിക്ലെയർ ചെയ്തിട്ടുണ്ട്. Okay, so when you take this test bench, you are giving value to the input in the test bench. You are applying values, test input values at the test bench. Okay, so our input values corresponding code and the data and the value should be called over there. Like that store input values store for what? Then only it will go to the design block, then where it will apply that value. So it takes some time. So always remember, when you write the test bench, all the inputs should be declared as registers by using the keyword in small letter reg. Okay, and then the input values നമ്മൾ ടെസ്റ്റ് ബെഞ്ചിൽ കൊടുക്കുന്നു. അത് ആ വാല്യൂ അതിന്റെ ഡിസൈൻ ബ്ലോക്കിൽ കൊണ്ട് അപ്ലൈ ചെയ്യണം. So it will take some time for that. So all the inputs that you are writing in the test bench should be declared as registers. Okay, then test benchലാണ് എന്ത് സംഭവിക്കുന്നത്? ഔട്ട്പുട്ടിന്റെ വാല്യൂ ഡിസ്പ്ലേ ചെയ്യുന്നത് അല്ലേ? So ഈ ഔട്ട്പുട്ട് നമ്മുടെ ടെസ്റ്റ് ബെഞ്ചിൽ വരുന്നു, അപ്പോൾ തന്നെ ഔട്ട്പുട്ട് എന്ത് ചെയ്യുന്നു? ഡിസ്പ്ലേ ചെയ്യുന്നു. So it just passes the values. So all the outputs are declared as wires in test bench using the keyword wire. Net and wire both are same. So you can use the keyword wire in small letters for declaring this wire data type or net data. So when you write this test bench, all the inputs in test bench, all the inputs should be written as registers. All the outputs should be written as wires. Okay, I repeat. I will just run this. And then write it once more. So, please note down this. We have design block as well as test bench. So, when you write programming, all the input ports should be declared as registers in test bench. Then all the output ports should be declared as wires. Okay. Then what about in the case of design block? Design block എന്താ ചെയ്യുന്നത്? Yes, test bench നുള്ള വാല്യൂ ഡിസൈനിലേക്ക് വരുമ്പോൾ അപ്പോൾ തന്നെ ബൂലിയൻ എക്സ്പ്രഷനിലേക്ക് ഇട്ട് കൊടുക്കുകയാണ് ചെയ്യുന്നത്. അല്ലെങ്കിൽ നമ്മൾ ഡിഫൈൻ ചെയ്തേക്കുന്ന ആ യൂണിറ്റിലേക്ക് ഇട്ട് കൊടുക്കുകയാണ് ചെയ്യുന്നത്. So all the inputs are declared as wires in design block. All the output declared as registers. Okay, and in Verilog HDL by default, all the ports are considered as wires only. നമ്മൾ ഡിക്ലെയർ ചെയ്തില്ലെങ്കിൽ അത് വയർ ആയിട്ട് കൺസിഡർ ചെയ്യും. Okay, and when you write the data flow model, since it is a continuous assignment, there is no need to declare. See, നമ്മൾ ഇവിടെ എന്താ എഴുതിയത്? ഡിസൈൻ ബ്ലോക്കിൽ ഔട്ട്പുട്ട് രജിസ്റ്റർ ആയിട്ട് ഡിക്ലെയർ ചെയ്യണമെന്ന് പറഞ്ഞു. It is not necessary in the case of, it is not needed in the case of data flow model. Why? Because this data flow model, we are using assign statement, that is continuous statement. So in this data flow model, no need to declare output as reg. Okay, but when you use behavioral model, it should be clearly specified in the design block. All the output ports are registers. Okay, when you write the behavioral model, it will be clear to you. So now just remember this much. When you write the data flow model, no need to declare this output and inputs as wires and registers when you write the design block. But when you write the test bench, it is compulsory. And the input values it will take some time for the processing. So all the input values must be declared as registers and all the output values must be considered as wires. Okay, now let's write the test bench. Next step, I think now it's clear to you. So the first step is module space module name 𝗲𝗏_TV. So here I am taking both the signals are of same type, small d and small a. So no need to repeat the code list over here. Next step is actually the syntax is output, then wire B input space reg A. Why? In test bench, all the inputs should be of register type, all the outputs wire type. So this is optional. Input and the keywords used over there, input and output. It was already we defined it in the design block. So just write wire B reg A. Then what was our third step? It is instantiation, that is connecting test bench with the design block that is to be tested. Okay, so the syntax to be followed is the module name that is used for the design under test, that is my node. So just write that name as such. Okay, then a label name, it will be N1. We are considering a single NOT gate, so let the label name be N1. So we are using this N1 over here. If in the circuit you are having a single NOT gate, then no need to write this label name. If it is a large circuit where you may have more than one inverter circuit, okay, then in such cases, N1, N2, then it should be specified over here, my node N1, my node N2, likewise. Okay, you see, it should be labeled clearly in the circuit and that should be used over here also. So the syntax to be followed is my node, that is the module name that we have used in the design block, space label name. Okay, label name means and we are giving some name, A1, A2, A3, like this. We are using a single logic gate, a single circuit only, then no need to write this label. Okay, then the port list that you have used in the design block. So if you are using, you can call it by two ways, either by order or by name. Okay, order means if you are writing B as first port here in the design block, the same should be written in the test bench also. So that this port, this output port will be connected to this output port. If you are writing A, B, then port mismatch occurs. That means B will be connected to A will be connected to B. So here this is output and input, isn't it? And here we have already declared B as the output and A as the input. And if you are writing in this order, then what this much will occur. Okay, this is called instantiation or port mapping by order. Okay, then the other method is called port mapping by name, where in that case no need to follow this order. I will show you what is this port mapping by order. Sorry, port mapping by name. So suppose I am writing the list as B, A. We are using different name. Okay, so wire B, reg A, wire means output, reg means input. Okay, then what do you mean by port mapping by name? Dot, syntax is dot A, in bracket, write the same port that is used in the same one, comma, dot B, in bracket B. See here, the first design block we have written B, A, but here in this instantiation process we have written A, B. That means we haven't followed the order, but here we have used the port mapping by name. Capital A is the input port that is connected to the input port of the design block. So the name which is written inside this bracket, it should be the name of the port which is used in the design block, or the module you want to connect. That name is to be given inside this bracket. Okay, so instantiation process is connecting test bench to the design block, where the syntax to be followed is module name, label name, module name, that is my node, label name, let it be N1, then port mapping by name, dot A, in bracket, the name, the same, the name that is used for the same port in the design block. Then dot B, in bracket B. Clear? So first step is module declaration. Second and third step, that is port declarations. Then the next step is instantiation. Okay, and the last step is applying test input vectors. For that, you can use the statements initial begin. Okay, initial begin, you are applying values to A. A equal to, let it be 1 tick B0. Okay, so this is called tick. Okay, this one represents size of the number, and this one, that is the number system. If you are using binary number, then it will be B. If you are using decimal, then you should write 1 big D. Okay, then this is the value that you are applying to this A. So, this meaning A is single 0 and assign. If you want to give 2-bit value, then how can you write 2 bit B00, or simply you can write 2 bit B0 or 2 bit B01. If you want to give 4-bit value, then the specification should be 4 bit B1001. So this is the way how the number system is specified in Verilog HDL. Here, in this circuit, we request only a single bit value. Hence, we have given here 1 dB0. Okay. So then after providing some delay, let it be 1 unit delay, you are again giving 1 dB1. You can give number of input test vectors as much as possible. You can give over here so that you will get the output with that much accuracy. 1 dB1. So you are giving first, initially you have given A as 0, right? In this step, after some time delay, you are giving 1. Then you are giving 0, then again you are giving 1. So your expected output should be negation of this A, right? So for this 0, your output should be 1. This one, output 0. This should be your expected output. Okay, so in this step, we are applying initial begin. Inside that, we will apply the input values. Then begin statement will be terminated by using keyword N. Then module statement terminated with N module. Okay, so there completes the test bench step. The steps of test bench. The steps are module declaration, code declaration, instantiation, that is just connecting, just linking the design to be tested. Then the next step, we will apply test input values. So for the current versions, no need to give this display instruction. Earlier case, we have to give the instruction like $display. But in current versions of simulation tools, when you simulate it, it will come automatically. No need to give this statement $display. So you can avoid that. So the last step is terminate the module. Okay, is there any doubt? Is it clear how to write the Verilog code for the NOT gate, that is design block as well as test bench? Thank you, sir. Am I audible to you?
Hello, clear ആണ് മിസ്. ഹലോ
ഹലോ,
ക്ലിയർ
ഡൗട്ട്
ആണ്.
ഉണ്ടോ? ടെസ്റ്റ് ബെഞ്ച് ചെയ്തതിൽ
ഇല്ല
ഡൗട്ട്
മിസ്സേ,
ഉണ്ടോ?
ക്ലിയറാ. ഇല്ല മിസ്സേ, ക്ലിയർ ആയി.
ഓക്കെ, സോ ഇനി ഇതൊരു EDA playgroundൽ next we will see how to simulate it in EDA playground. Before that, shall we have a break? Please, sir.
Hello, miss.
കേൾക്കാം സർ, കേൾക്കാം. 10 minutes break എടുത്തതിൽ
എത്ര
കണ്ടിന്യൂ
മിനിറ്റ്
ചെയ്യാം.
എത്ര മിനിറ്റ്? 10 minutes. Okay. Okay, okay.
Prajeesh sir, shall we continue? Shall we continue the session?
Okay. Okay.
So I think now let's do the simulation for the same circuit for the NOT gate using EDA playground. I think all of you are having a net facility. Register playground continue ചെയ്യാലോ അല്ലേ?
നെറ്റ് ഉണ്ട് മിസ്സേ, കുഴപ്പമില്ല.
So now let's see how to simulate the same circuit. That means so far we have written the Verilog coding for the NOT gate, right? So now let's see how to simulate the same using EDA playground. Okay, so EDA playground is just like a playground itself. No need to have account and all. If you are having Google mail ID or Google account is there, then you can directly log on to that EDA playground. Then you can directly paste your code over there. Then see the result. Okay. Now let's see how to simulate the NOT gate Verilog code using this EDA playground. So for that, just go to Google page. There you can type EDA playground. You can search for EDA playground. Is it visible to you? Clear ആണോ? Google EDA playground just type.
അതെ.
Okay. Then there, just click on that Verilog system Verilog, or just go back. Then EDA playground edit code. So just go to the Google page, type EDA playground, then the first link, that is www.edaplayground.com. So where you can have EDA playground edit code, just click on that. Then you will have a page like this. Edit page which has got two sides. On the right side you can write the design block. So we have written the design block for this. If you have written in your Notepad, you can directly copy your code over to this page. So module space minor bracket B comma A. Then every line should be terminated with a semicolon. Then first step was module declaration. Second step output space B. Next step input space A. Then next defining functionality using any of the modeling. So here we have used the simple model that is Dataflow model as same B equal to. Then negation operator is there. The key above the tab button. Okay. Shift key. Shift അടിച്ചിട്ട് ടാബിന് മുകളിലുള്ള key, that is negation operator, negation A, terminate with semicolon. Then terminate the module using the keyword. It should be written in lowercase. There is no space in between. End module, end and module should be written together. That is end module. Okay. Then now on the left side we can write the test bench. Okay. So test bench. The first, what was the first line? First step was module declaration, right? So module space, let the module name. You can give any name over there other than the name of the basic gate, the name of the basic gate as such. So module space, module name, minor underscore TB. And minor underscore TB module name declare. You can give any name over there other than not as such. Not get the message. Okay. Then all the inputs should be declared as registers using reg in the test bench. So reg A, next step wire and wire is wire output is B. So wire B. Then design to be tested, design under test or unit under test, that is minor. Its module name is minor. So minor space N1 in bracket. Let us instantiate or call by order. So let me write the same order that we have written in the design B, comma A. Okay. Then initial, then begin, A equal to 1 peak. This peak is use in the key just left side apostrophe. Tick A equal to 1 tick B 0 semicolon. Then provide a delay for applying the next input. So the delay can be provided by using hash 1. That means 1 unit delay is provided. If it is hash 2 unit delay provided between 2 successive input signals. So hash 1 space A equal to 1 tick B 0. Okay, hash 1 A equal to 1 tick B 1. Okay. If you give more and more inputs, then your output will be that much accurate. So 0, 1, let me give it as 0. Then this loop should be terminated by using end statement, and finally end module. Okay. Then when you on the left side you can see these languages, these icons such as languages, tools and simulators, examples, community, etc. Right? Is it visible? Just select this tool. Then on tools and simulators, select and take the first option. Then click on, just give a tick mark on open 𝗙𝗡𝗏 after run. Am I clear to you? repeat Prajeesh sir. Okay. So select any one tool under tools and simulators. So far we have selected the first option. Then click on open 𝗙𝗡𝗏 after run. Okay. Then click the save button. Okay. Then it will shows the message like you must log in before running or saving the playground code. Okay. So login. Just select login. You can log in with Google or log in with Facebook, or you can create an account over there. So if you have the Google account, Gmail account, log in with Google. My Google account is already open here. So if it is not login, then it will ask the password. Then type your password and log in to your Google account. Then it will automatically come to this EDA playground page. Okay. Okay, sir. Then before running this code, we have to include one more step in the test bench. That means on the first line, we can specify the or we can define the time scale unit. Okay? What is time scale unit? Time scale means in the Verilog simulation, it depends on how the time is defined. Why? Because the simulator needs to know what actually see here we have provided #1. One delay is provided between each input vectors. Okay, so the simulator should know what does it mean. What does this #1 means? Okay, so it should be converted in terms of time. Okay, so for that we can use a compiler directive so-called tick time scale. Okay, so this tick time scale gives or specifies the time unit and the precision of that unit. That means I will show you. See, for defining time scale or for defining time scale unit, we can use a compiler directive. It is called tick time scale. So this is called tick. Okay, അതിനെയും tick എന്ന് തന്നെയാണ് നമ്മൾ വിളിക്കുന്നത്. പക്ഷേ നമ്മൾ ടൈപ്പ് ചെയ്യുമ്പോൾ this tick value should be given by using the key which is just above the tab. ടാബിന് തൊട്ട് മുകളിലുള്ള കീയിൽ ഒരു സിമ്പിൾ ലൈക്ക് ദിസ് ഇങ്ങനെ ഒരു സിമ്പിൾ ഉണ്ട്. സോ നമ്മൾ ടാബിന് മുകളിൽ നമ്മളിപ്പോൾ കുറച്ച് മുമ്പേ നെഗേഷന് വേണ്ടിയിട്ട് ഷിഫ്റ്റ് അടിച്ചിട്ട് നമ്മൾ ആ കീ സെലക്ട് ചെയ്തായിരുന്നു. Without choosing shift, we can when you use directly that, you will get this tick value. Okay, so നമ്മൾ enter കീയുടെ ലെഫ്റ്റിലുള്ളതാണ് എന്ത് സൈസ് സ്പെസിഫൈ ചെയ്യുമ്പോൾ നമ്മൾ യൂസ് ചെയ്യുന്ന tick value. സോ ഈ ടിക്ക് ടൈം സ്കെയിലിന് നമ്മൾ യൂസ് ചെയ്യുന്നത് എവിടെയാ? ടാബിന് അല്ലെങ്കിൽ 1 എന്ന കീക്ക് ജസ്റ്റ് ലെഫ്റ്റിലുള്ള കീ നമ്മൾ എടുക്കുന്നതാണ് ടിക്ക്. Okay, so the syntax to be followed while writing this compiler directive tick time scale is tick time scale Then specify the time unit. Then give a slash. Then specify the time precision. First, you are specifying the time unit, then give a slash, then time precision. For example, if you are writing tick time scale 10 nanosecond bar 1 nanosecond. What does it mean? The total unit is 10 nanosecond and each unit with a precision of 1 nanosecond. Is it clear to you? So, if you are using tick time scale 1 nanosecond bar 1 picosecond. So, the total unit will be 1 nanosecond. Then, in that, this unit have the precision, or each unit will be of 1 picosecond. Okay, so by defining this time scale compiler derivative, we can compiler directive, the simulator will know how the delay can be specified in terms of time. Okay, I think now it's clear to you. So just specify the time scale on the first line of test bench. Pick time scale space 1 nanosecond bar 1 picosecond. No need to use semicolon in that line. So first line time scale compiler directive define cheyna line no need to use the semicolon. Okay, now just save the code, then click on run. If see here the one error, it shows one error. What is that error? .bcd file, no .bcd file. Okay, that means when you simulate this EDA playground, what all input variables will be given in your design unit as well as in test bench, it should be dumped onto a folder called $dump file. Okay, now we EDA playground മാത്രം ചെയ്യുമ്പോൾ ഒരു process ആണ്. It will all the changing values will be dumped to the file called $dump file. Okay, and it has got an extension of .bcd. BCD means value change dump. That means what all values will be changed, that will be given, that will be saved or stored on a file so-called $dump file. Okay, so we should declare that $dump file when you use the EDA playground. But if you are using the simulation tool as model sim or lattice diamond, no need to write this .bcd file over there. Okay, it will not be saved in the BCD files when you use the simulation tools like model sim or lattice diamond or silence tool or quartus. In all those cases, no need to use this BCD file. But here in EDA playground, you should declare BCD file. So its declaration goes like this: initial, begin. Let me write it on the word page for the. Then it will be more clear to you. So, how to write the, or what is the syntax for declaring BCD file. Okay, it's initial, begin, okay, dollar, dump, file, double quotes inside, double quotes, dump.bcd. Okay, then dollar, dump, waves. That means the changing values. What are values? Changes should be declared as dollar dump was initial, begin, end. Okay. So initial, begin, then decisions. Dollar dump file. Dump.bcd. Okay, so make it semicolon, then dollar dump first. Finish. Yes, since we don't have any other errors in our code, when you declare the VCD files, the output waveform will be opened, and from there, when you drag the cursor, you can see its values. Or on left side in orange color, you can see the respective values. So initially we have given. When you minimize this window, you can see your code. So initially you have given A as 0, right? A as 0. So when you give 0 as the A input, output, expected output is 1, isn't it? So here we have obtained the output as 1. So for next unit, after 1 unit delay, we have given A as 1, right? So A value is 1, B changed to 0. Next, third phase, A is 0, B is B, then B value should be equal to 1. So our design is correct. So what is the next step? If you want to burn it on a FPGA kit, now simulation wise everything is okay. Then if you want to synthesize, just take this design, then put it on the Xilinx tool, okay, or Quartus tool. Then from there you can synthesize it, and finally you can burn it. You can interface it to the FPGA kit or Spartan kit. Okay. Then if you are using Quartus, then where we are using the board as Cyclone. Cyclone board will be used over there. In Xilinx, we will use Spartan kit. Okay. So where you can see the actual hardware output. Okay. So when you use this synthesis tool, what happens is the corresponding logic level circuit will be automatically generated at the back side, at the back end. Here actually what we did was we have just written the Verilog code and we have checked its output. Okay, so if you want to have the hardware implementation, what we do is we will take this design unit and we will compile the same process. We will compile it, and if it is error free, then you can synthesize that. Then finally, it will be interfaced onto the Spartan kit. If it is a case of Xilinx tool or Quartus tool, we will use Cyclone. Okay, so where what happens is the inside that board the security block will be reconfigured with respect to your design unit. അല്ലെങ്കിൽ നമ്മൾ പറഞ്ഞു ഓട്ടോമാറ്റിക്കലി ഒരു സർക്യൂട്ട് ഡെവലപ്പ് ചെയ്തെന്ന് പറഞ്ഞു. ആ സർക്യൂട്ടിനനുസരിച്ചുള്ള ഒരു ബ്ലോക്ക് എന്ത് ചെയ്യും, ഈ നമ്മുടെ ബോർഡിൽ ഹാർഡ്വെയർ ബോർഡിൽ എന്ത് ചെയ്യും, ബേൺ ആകും. ഓക്കെ, സോ നമ്മൾ ഈ കൊടുത്തേക്കുന്നത് പോലെ എന്ത് ചെയ്യും, when you give the inputs, അവിടെ നിങ്ങൾക്ക് inputs you can apply through the switches. So with respect to that you can see the correct output on the board. Okay, ഇപ്പോൾ നമ്മൾ സിമുലേഷൻ റിസൾട്ട് മാത്രമേ ചെയ്യുന്നുള്ളൂ. Okay, now I think let us do another code, that is Verilog code for 2 input AND gate. Verilog code for 2 input AND gate. Verilog code for 2 input AND gate. So for that, what is the first step? First of all, just draw the block diagram. Actually, it's called black box. Okay, it is black box is nothing but just the block level representation of the circuit to be the same. So I am giving just the name as AND2 gate. Okay, let the inputs are A, B, output let it be C. Okay, so can you try it yourself? So take EDA playground, just remove, okay. So here I have chosen the module name as AND2 gate, AND2 gate. Then let the signals are C, A, B. Okay, let us give in other way. First input A, B, C. Then inputs are A, B. Output endana? Output C. Okay, so for knowing the operators, you should study the Verilog syntax. I told you it is clearly given in this textbook of 𝗙𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏 vertical, we want AND operator, bitwise AND operator. See the symbol ampersand. For OR operation, vertical bar. For exclusive OR, it is in the vertical cap. Exclusive NOR, negation of vertical cap. Okay, so ampersand is used for load for AND operation. So assume our output is C equal to what was that? A ampersand B. So where completes the circuit functionality definition using Dataflow model, then N module. Okay, then respective test bench. Let the module name be my and underscore TB. Then inputs are A, B. Output S, Y, and C. Then we have given module name as and to gate. Okay, since it is and N1 തന്നെ കൊടുത്താൽ മതി. This for a change I am giving here A1 as the label name. Then the order we have given for the port list in design block is A, B, C. Clear? Then here the input vectors. What should be our input vectors? We want to check the operation of AND gate. How can we check its operation? Yes, you know how to write the truth table. You know its truth table. Okay, so A, B, C. If any one of the input is 1, if any one of the input is 0, output will be 0. 0, 1, 1, 0, 1, 1, 0, 0, 1. So if both are 1, then only output will logical 1. So just give that truth table in our test bench. Then in the output, when you obtain the output waveform, just verify its truth table. Okay, so A equal to 1 tick B 0. What is B? 0 for 0 0 condition. B equal to 1 tick B 0. Okay, then 0 1 condition. A equal to 1 tick B 0. B equal to 1 tick B 1. Okay. Next is 1 0. B equals 1 tick B 0. 1 1 condition. For the 1 1 condition, both should be equal to 1, right? That is A equal to 1 and B equal to 1 tick B 1. Okay. So here we have given all the 4 conditions, all the 4 states 0 0, 0 1, 1 0, 1 1. Okay, then save this. Let's see whether it is working properly or not. Just run. See, for A and B 0, output C equal to 0. For 0 1 condition, output 0. Then 1 0 condition, C equal to 0. Then 1 1 condition, output is 1. It's correctly working here, right? Any doubt?
Teacher,
I can hear you.
vector more
More
than
than
bit.
More than 1 bit, yes. So let's see how to declare the given signals. Given ports are vectors. Okay. So very good doubt. See here we have considered 2 signals A, B, right? So and here we declared A as a single bit signal. How can you say that this is single bit signal? In the test bench, we have given the value as 1 tick B, right? That means binary value 0 of single bit size is assigned to A. That is, A is declared as a single bit port, single bit signal. B also declared as a single bit signal. Suppose I am taking a variable A. A മാത്രമേ select ചെയ്യുന്നുള്ളൂ and I am declaring this A as a vector instead of a single bit. I am declaring this A as a vector. Okay, so how can you write that A as in vector form S. See in my program, I am planning to design A as a vector. So this A should have size 2-bit. Why 2-bit? Here we consider A as the input and it has got 2 input signals. Okay, so run input signal on the, but anyhow we already considered a single input signal. So how can you represent that single input signal with 2-bit value? Yes, nothing but the vector representation. So instead of writing this A and B separately, you can name it as A of 0 and A of 1. Okay, so what are changes to be made in your program? See, we don't have any B signal now. Why? We are planning to represent this A as a vector form. Okay, so just remove B signal. Here also, the syntax to be followed for the vector representation is, if it is a 2-bit size, here we have input signal, right? So specify the type of the port. Here we have input port. Okay, so just use the keyword input, then specify the size in the square bracket. Okay, where either you can write MSB colon. Here we want to have 2-bit size. So 2-bit size means A of 0 is the LSB, A of 1 is the MSB. So either you can represent 1 colon 0. It means 1 represents the MSB, 0 represents the LSB. In another way, you can refer it as 1 down to 0. Or you can represent it's just like LSB colon MSB. It is called 0 down to 1. Okay, so in this representation, it completes its declaration by specifying the variable A. So your instruction meaning in the here we have declared A as the vector, and this A has got 2-bit value such as backend automatically A എന്ന് പറയുന്ന സിഗ്നലിന് 2 location allocate down such as A of 1 and A of 0. So when you write it on the code, input space 1 colon 0, 1 colon 0 A. Okay, then here you should write A of 1, A of 1 ampersand A of 0. Okay. Then here also we have A and B is not there. Then B is not there. So reg representation also should be changed as vector style, that is reg 1 down to 0. Okay. Then while C A1, AC. Here instead of writing A, B, 0, 0, directly you can represent A equal to 2 tick, B 0. Since both the values are 0, no need to write two zeros over there, just write single 0. So it gives 0 value of two sides, that means A equal to 0, 0. Then next step you can give A equal to 2 tick, B 0, 1. One zero, then 1 1. Save. Zero zero 1 0 2 0 3 1. So here see in EDA, when though we are giving 0 0 0 0 1 1 0 1 1, it gives the decimal representation, that is 0 1 2 3. Okay, but when you simulate the same on the model sim, where in the waveform you can have the values as A of 0 0 0 1 1 0 1 1. Instead of this 0 1 2 3, you will have 0 0 0 1 1 0 1 1 like that. Okay. Anyway, by vector representation also, our code is perfectly working. Any doubt? Okay, thank you, Vidya. I hope this is clear to you. Okay, now let's move on to another circuit. So, can you try to write the Verilog code for full adder using half adder? I will show you the diagrams. Then it will be more clear to you. From this diagram, how can you write the code for full adder using half adder? What is the time now? 12:25. So, shall I explain it with model sim, Prajeesh sir?
പറയുന്നുണ്ടോ സീക്വൻഷ്യൽ?
സീക്വൻഷ്യലിന്റെ ജസ്റ്റ് ക്ലോക്ക് ജനറേഷൻ, ജസ്റ്റ് ഡി ഫ്ലിപ്പ് ഫ്ലോപ്പ് ഒരു ടെസ്റ്റ് ബെഞ്ചിൽ മാത്രമല്ലേ ഉള്ളൂ ഡിഫറൻസ്. അതുകൂടി ഒന്ന് ചെയ്ത് കാണിക്കാം. മോഡൽ സിമിൽ പ്രൊസീജിയർ എഴുതിയെടുക്കാം, നോട്ട് ചെയ്യാൻ പറ്റുമല്ലോ. So when the student edition is available in the net, I will inform you so that you can download it from the net. You can use it for 6 months. 6 months if you want, you can take the the trial version again from the site. Okay, model sim. I think here in our lab we are using model sim. Using model sim, we are doing the simulation, and for the hardware implementation, we are using this Ultra Corpus 2. So the already open source site available ആണ്. നമ്മൾ ഹാർഡ്വെയറിന്റെ ആ ഒരു കിറ്റ് മാത്രം പർച്ചേസ് ചെയ്താൽ മതിയാവും. So I think I can go ahead with the model sim procedure. Okay. So for that, the first step is that we should create one directory or one folder in any of the drives. So let me create one folder in the desktop. So this is the first step. So now I am explaining how to run a given window code using model sim software. How to simulate the given window code using model sim software. Okay. So first step is create one directory. Okay, it is nothing but a folder is creating in any of the drive. So here now I just created one folder named DRS in the desktop. Okay, so next step is just open your model sim. So I have already downloaded, I have the cracked version of this model sim Ultra 10.1 version. Just opening that. Okay, the next step is take file, change directory, and select the folder that you have created in the location in the drive. So here I have selected DRS from desktop, then OK. So at the bottom you can see a transcript window. Okay, where if you want you can check your directory by typing pwd, present working directory. Just type enter. So it shows the path user staff desktop DRS. So now we are working in our own directory. Okay, then next step is file, new project. Next step is to create one project. Okay, second step, open model sim, then change directory. Okay, change directory, then change directory, select your own directory. Then the third step is create project. So inside this project, you are creating your own, you are designing a given logic circuit, given digital circuit. Okay, so create project. So just give any name over there. I am giving my programs. Just any name you can give it over there. Okay. Then a small window comes. The next step is to create file. Create file. Okay. So just already we have and to gate code, right? So I am just giving that code. So no need to give extension over this, but for the safety, just give .b. Because for VHD, we are normally use .VHD as the extension. And here just select file as type Verilog. Okay. So creating a file named and2get.b Verilog. Okay. Just double click on that. Then editor window will comes. So already we have the code for this and2get. Just copy. If you don't have, you should type, you can edit whatever you want over here. So you can write the video code over here. So I am just saving. Okay. Then the next step is again take file, new source Verilog. Okay. So create file. So where the same block created, then other save edu. Next step file source Verilog. File new source Verilog. New source Verilog. File new source Verilog. Okay. So just taking file new source Verilog. Then another editor window will comes with name as untitled. Okay. Just we have the test bench also here. Just copy down that. Type scale. So as we discussed here in Modelism, we no need to have this dump files. Okay, so you can remove that one. Time scale 1 nanosecond per 1 microsecond. Module declaration, code declaration, instantiation, applying testing to vectors, module termination, then save. Then a window will comes. So where you can give the file name. I am just giving and2get underscore pb. You need to give the same module name. If you want, you can give different name. Okay. .b is Verilog file. So .b as the it is already saving as the type of .b. Okay. So see in this workspace on this left side when you check, there is only one file in that workspace. But here we have created two files. One is design block and another is test bench. So what we need to have, we want our test bench also in this space. For that, what we do is add to project existing file. Okay. Then test bench created and saved. Then എന്താ ചെയ്യുന്നത്? Workspace, workspace, add to project existing file, add ചെയ്യുക. Okay. So right click, add to project, existing file, browse, add to gate, open, add file as type, just choose the option Verilog. Okay. Now what is the next step? Next step is compilation. Compilation, next step, simulation, then add sequence to wave, run. Okay, these are the steps to be followed while simulating Verilog coding models. So, what was the next step? Compilation. So, compile all. If everything is correct, then you will get a message in green color to compiles. Compilation was successful. If any error occurs, then comments will comes here in red letter. So then when you click on that, see here, 2 compiles, 1 failed with error. So our AND has got 1 error. Okay. So when you drag your mouse here in transcript window, you can see that compile of AND gate failed with 1 error. Then just double click over there. So it will clearly specify what is the error comes in the specified file. So here in our design block, we have 1 error that is at 4th line. Okay, so just check your 4th line and see extra semicolon comes, so just remove that, save. If you want, you can compile the selected file. Just select that, compile selected. So both are correct now. So if it is correct, then a tick mark, green color, tick mark will comes. Next, simulate, start simulation, work, my and GB. Okay. But I can save. And wave. This is the run button. So the last step was add sequence to wave. Just right click on here, add to wave, all items in region. Then all the variables that you have declared in the test bench will come over here. Then run button, run all. Okay. So you see the result. See, initially we have given 0, 0. Can you compare the results of model sim simulation and VDA playground? in EDA playground where we have the specification of A as 0, 1, 2, 3. That means if we represent signals in vector, it will give its corresponding binary values. See here in model sim, 2-bit representation. In the test bench, we have written it as 2-bit B binary value. So 0, 0, 0, 1, 1, 0, 1, 1. If any one input 0 for the AND gate, output 0. And finally, for the last case, we have the logic 1 output. Okay, so this is a procedure to be followed when we use the model sim software as the simulation tool. That is a
Okay, ma'am.
next program shall we proceed with model sim or ADA playground? Which one you wanted?
Ma'am.
Model sim.
Hello. Model sim.
Model sim മതിയോ? Okay. So നമുക്ക് അടുത്തൊരു പ്രോഗ്രാം ഇനി ഒരു സീക്വൻഷ്യലിന്റെ ചെയ്ത് നോക്കാം അല്ലേ? കാരണം സീക്വൻഷ്യലിന്റെ ടെസ്റ്റ് ബെഞ്ചിൽ കുറച്ച്
Okay, okay.
Okay. Okay, thank you. So next we will see how to write a sequential circuit, how to simulate a sequential circuit using model sim software. So for that, okay. Let's see the coding of a small circuit, that is let it be D flip-flop. Let's see the coding of a D flip-flop. The same procedure to be followed for writing the large circuit also, large sequential circuit also. So now let's see another new project. Sequential circuit. Create new file. Let it be my flip-flop. So add file as type Verilog. Okay, here also, you know what is D flip-flop? D flip-flop with respect to the clock signal. Okay, with respect to the clock signal, whatever value, that means here you can give either positively edge triggered clock pulse or negatively edge triggered clock pulse. Okay, so in your program, you will, if you are giving if you are considering positively edge triggered clock pulse, then you can have the D flip flop output with respect to the variation of that clock pulse. That means whenever your clock pulse signal becomes positively edge triggered, then your D flip flop output will be the data input itself. Okay, so for writing that code, let's start with module my D flip flop. Okay, let the input is D, then you have a clock signal, then the output is Q. Okay, then our inputs are input space D comma clock. Okay, then output is Q. Okay, then here one point to be noted is that we already discussed that other than Dataflow model, when you declare output signal into the same block, it should be declared as reg type. Specifically, when you write the when you design sequential circuit in 𝗩𝗏𝗿𝗂𝗍𝗔𝗐, you should use behavior model. Because why? Because in sequential circuit, it depends on the value of clock signal. So clock signal is continuously changing. So with respect to the value of clock signal, every moment the input value, the output value also changing with respect to that clock signal. Okay, so when you write the code for sequential circuit, you should use behavioral model, and in that behavioral model, the output signals should be declared as reg type. It should be noted that output should be declared as reg type. Okay, so in Dataflow model, we use the keyword as assay. In the Dataflow model, we use the signal as assay. Okay, when you use behavioral, the syntax to be followed is always at the rate. Let me consider positively edge triggered clock. So pos edge clock. Okay, pos edge clock. Same. We can directly give it. The clock comes whenever clock comes positively edge triggered. Assign Q equal to, that is Q equal to your data input D. Okay, then N module. Okay, this is a small circuit. If you are considering reset value, then the code should be always at pos edge clock or pos edge reset. These signals are called sensitivity signals, or the signals written inside this bracket is called sensitivity list. That means when you write the behavioral model, the syntax to be followed is use the keyword always at the rate. It is followed by sensitivity list. Sensitivity list. What is sensitivity list? The signals which are keep on changing should be included inside this sensitivity list. Okay, if you are considering reset also, the syntax will be pos edge clock or pos edge reset or neglect reset. Then if reset, if more than one statement comes under this always, then it should start with a begin statement. Okay, so always begin if reset output equal to 0, else output equal to D. Okay, so we are considering only clock signal. Then we have written its design block. Then what is next? Next is we have to write its test bench. For that, file, new, source, Verilog, where you should write the test bench of the D flip-flop. So module D flip-flop underscore TB. Okay, then reg clock, comma D. Okay, then output signal was Q, so wire Q. Then what was the name? We have used my DFF. So for instantiation, you should use the same name, my DFF space. Let the label name be F1, then port list. Let us use instantiation by order D clock Q. So D, comma, clock, comma, Q. Okay. Then terminate with semicolon. Then apply in test vectors initial, begin. So here we have to generate the clock signal. So for the sequential circuit, the main difference is that, or the extra step, one more step comes while writing test bench. That is, you should write the clock generation unit, clock generation steps in the test bench. So initial begin, clock is initialized as clock equal to 1 bit B 0. Then what is the next step? We can use a repeat loop. Repeat all the syntax and all. You can refer 𝗙𝗏𝗏𝗏𝗏 textbook. So for repeat, for defining repeat loop, you can use the keyword repeat, then #5 clock equal to negation of clock. Initially, we clock 0 ആയിട്ട് set ചെയ്തു. Then for every 5 unit delay, what happens is clock signal negate ചെയ്തുകൊണ്ടിരിക്കും. Alternate value, അതായത് അതിന്റെ complement value കിട്ടിക്കൊണ്ടേയിരിക്കും for every 5 unit delay. So ആ ഒരു cycle 10 times repeat ചെയ്യും. If you want, you can give more value over here, so that you will have more and more clock generation cycles in your simulation unit. Okay, so initial begin clock equal to, then begin end ചെയ്യുക. Okay, then next എന്താ ചെയ്യണ്ടേ? ടെസ്റ്റ് ഇൻപുട്ട് വാല്യൂസ് കൊടുക്കുക അല്ലേ? സോ ഡിക്ക് വാല്യൂ കൊടുക്കുക initial begin B equals 1 bit B 0 or 1, you can give it be 0. Then after 1 unit കൊടുത്താൽ പോരാ, നമ്മൾ ക്ലോക്ക് ജനറേഷന്റെ ടൈം ഡിലേ നമ്മൾ 10 എന്നാകും. അതായത് ഫോർ എവറി 5 units it is keep on changing. So ആ ഒരു 5-നേക്കാട്ടിൽ കൂടിയ വാല്യൂ കൊടുക്കണം. So it will be #10 B equal to 1 bit B1. Okay, then just go here, just here. and the module. So module declaration, code declaration, instantiation, clock generation, then applying test input vectors. Okay, so just save. So my 𝗙𝗏_tv.me, then right click and the project existing file, browse my 𝗙𝗏_tv was our test bench file. Just select that. There you go. Okay. Then compare all. Okay, test bench clock does not refer to a scope. Next step is simulation. Start simulation. DFFTV. Okay. Then add signals to wave. അതിന് വേണ്ടിയിട്ട് ഇൻസ്റ്റൻസ് എന്ന് പറയുന്ന ലെഫ്റ്റ് സൈഡിൽ കോർണറിലുള്ളതിൽ DFF_TV, our test bench file is there. Just right click over there, select add to wave all items in region. Then your signal comes over there. See, whenever post edge comes എന്ന് പറഞ്ഞാൽ എന്താ positively edge triggered level, positively edge triggered, that means clock equal to 1. Okay, so negatively edge triggered means clock value should be equal to 0. So clock 1, our D value equal to 1 ആണ്. So at the same time Q output എന്താ കാണിച്ചിരിക്കുന്നത് ST1, that is signal test 1. Okay, whenever clock comes positively edge triggered, D equal to 1, output also equal to 1. Okay, now see, clock equal to 1, D value equal to 0, and Q also equal to 0. So our circuit is properly worked as a D flip-flop, or you can say, you can call it as, I think we can call it as delayed flip-flop or data input flip-flop, right? So നമ്മൾ കൊടുക്കുന്ന കണ്ടീഷൻ അനുസരിച്ചിട്ട് ക്ലോക്കിന്റെ വാല്യൂ അനുസരിച്ചിട്ട് we will have the data input at the output side. Clear? Is it clear to you? Any doubt in this models and simulation? Am I audible to you?
Hello, Miss. Clear ആണ് Miss.
Okay, clear ആയിട്ടുണ്ടോ?
അതെ അതെ.
Okay, so നമ്മളിപ്പം it has seen how to write the Wavelet code for a given digital circuit. That is, we have seen both for the combination circuit as well as sequential circuit using EDA playground as well as the models. Okay, so one more thing is there, how to code structural style of modeling. Nowadays, switch level is not at all used because it is. Is it clear to you?
അതെ അതെ കാണാം Miss. Clear ആണ്.
Okay, okay. So, already we have discussed data flow modeling as well as behavioral modeling. In data flow, we will use assign statement, and behavioral, we can have this always statement. Okay, so if you want, in behavioral modeling, one more thing is there to remember. Under this always statement, if you want, you can have loop statements such as case loop, if else loop, for loop, and all. If you want, you can write it over there. Okay, then how can you write a structural style of model? എങ്ങനെയാ structural code എഴുതുന്നതെങ്ങനെയാ? So ഈ EDA playground ൽ തന്നെ ഞാനൊന്ന് change ചെയ്യാം. See, already we have code for AND 2 gate. So output C input 1.08, then just instantiate AND gate in the structural step of model. That is, the syntax was like and space A1, then A, okay, output component is library. Already it is written the order line output of input. So C comma A, C comma into semicolon. Check. See here, what we have done here is we have written the code in terms of in structural style of modeling. What is structural style of modeling? You have a digital circuit design. You will draw the logical gate diagram, logical level diagram of the given digital circuit. Then normally we will use you can have any gates, that means AND gate, OR gate, NOR gate, XOR gate. Whatever be the gate used over there, you should call the respective gate by its name itself. See, ഇവിടെ നമ്മൾ AND ഗേറ്റിനെ small a and b and then തന്നെ യൂസ് ചെയ്തിരിക്കുകയാണ്. That's a type of instantiation or port mapping. അല്ലെങ്കിൽ നമ്മൾ കോൾ ചെയ്യുവാണ്. Why? Because is inside the standard library of model sim, all the basic gates are well written over there. So when you use structural style of modeling, first of all draw its respective logical level diagram. Then use if you are using a diagram that consisting of more than one AND gate, then what you want to do is call AND gate, that much times over here. That means if 3 AND gates are used, then you should call AND gate 3 times. Okay, മനസ്സിലാവുന്നുണ്ടോ? Then ആ logical diagram നമ്മളിപ്പോ let me show you the diagram. For example, see, it will be the circuit diagram. നമ്മളൊരു logical diagram നമ്മൾ consider ചെയ്തിട്ടാണ്. Suppose if you want to write the structural level of code for this circuit, how can you write that? Yes, just give the name as A1, A2, O1. Okay, 3 gates, 2 AND gates and 1 OR gate. That the inputs are A, B, C, D. And output of A1, let it be Y1, output of A2, Y2, then final output Y. Okay, so first step, you all know how to write the initial steps, module declaration, code declaration, then end module. So for the circuit functionality definition, if you are using structural modeling, how can you write that? Yes, for the first AND gate, use AND A1, and inside that first you should write the output. So this order should be followed by writing the standard codes, means the codes written in the standard library. So Y1, A, B. So നമ്മൾ ഈ ഒരു ഡയഗ്രത്തിന്റെ ഇത്രയും കംപ്ലീറ്റ് ആയിട്ട് ഇവിടെ ഡിഫൈൻ ചെയ്തു. A1ന്റെ ഔട്ട്പുട്ട് ഈസ് Y1, ഇൻപുട്സ് ആർ A, then next AND is A2, so its output is Y2, then C and D are the inputs. Okay, then OR gate in small letter called the standard OR gate written in the library of Model. So OR, O1, Y, OR the inputs എന്തൊക്കെയാണ് Y1, Y2. Okay, and you can see that Y1 and Y2 are interconnections, right? So it should be declared as wire. Or by default itself, it will consider as wires. Okay, when you write the respective test bench, this Y1 and Y2 also should be declared as registers in the respective test bench. നമ്മൾ ടെസ്റ്റ് ബെഞ്ച് എഴുതുമ്പോൾ ഡിസൈൻ ബ്ലോക്കിൽ എന്തൊക്കെയാണോ ഇൻപുട്ട് അതിനെല്ലാം നമ്മൾ അതിനെ റിച്ച് ആയിട്ടാണ് ഡിസ്ട്രിബ്യൂട്ട് ചെയ്യുന്നത്. So all the interconnections are considered as wires in the same block. So when you write the respective test bench, it should be declared as rich in the test bench. Is it clear? Structural style of modeling clear ayo?
Okay, miss.
Okay. If you have any doubt, you can ask me now.
Okay.
We have got a comment like it's very difficult for us to grasp everything in one day. Yeah, it's true. So, let's start here. If you have
Okay,
any doubt, you can reach me. You can mail me to my mail ID rsdivya@𝗙𝗏𝗡𝗎𝗏. You can ask me.
ഞാൻ മെയിൽ ഐ ഡി കൊടുക്കാം മിസ്.
Okay.
ഡൗട്ട് എന്തെങ്കിലും ഉണ്ടെങ്കിൽ ചോദിക്കാം കേട്ടോ.
Okay. ഇതിന്റെ സിമുലേഷനും ഇതിന്റെ എന്തെങ്കിലും ഈ കോഡിംഗ് ഒക്കെ ആയിട്ടുള്ള ഡൗട്ട്സ് ഉണ്ടെങ്കിൽ യു ക്യാൻ റീച്ച് മീ. രജിസാന്റെ ഫോൺ നമ്പറും മെയിൽ ഐ ഡി ഒക്കെ ഉണ്ട്, നിങ്ങൾക്ക് എന്നെ കോൺടാക്ട് ചെയ്യാം. ഓക്കെ, താങ്ക് യു.
ഓക്കെ, ഞാൻ പറയാം മിസ്. ഓക്കെ, നമുക്ക് വൈൻഡ് അപ്പ് ചെയ്യാം. ഓക്കെ ഓക്കെ. ഹലോ
Hello.
ഓക്കെ മിസ് എന്നാ കൺക്ലൂഡ് ചെയ്യാം.
Ah.
Okay. Okay, ma'am. I would like to thank our guest, Ms. Divya Miss of 𝗙𝗪𝗔𝗿𝗍𝒑 College of Engineering for today's FTP. Thank you for your very interesting and informative session. Miss has given a very good coverage on Verilog coding, and I am sure all the participants have benefited from this FTP. Thank you, ma'am, for this wonderful session. And I thank all the participants for your kind cooperation. Okay. Thank you, ma'am.
Okay, thank you.
Okay.
Thank you all.
Okay.